Good evening, my name is Renu Raman Sahu, and today we will be discussing about the physics of materials, the third week. So, what in this week we did was to develop a model. The model that we developed is called Drude-Lorentz model, and using this model, what we did, we used the laws of ideal gas, where ideal gas means the particles are non-interacting with each other, and these are the classical particles, and we used the laws which govern this ideal gas and imposed it on the electrons, and based on that we tried to get some properties. So, here we will try to understand three different properties. One is electrical conductivity, then the thermal conductivity, and the third is the relation between electrical and the thermal conductivity, that is called Wiedemann-Franz law. So, let us first look at the electrical conductivity. So, given a material, what is it that we are quite interested in? Like when it comes to the electrical conductivity, the very first experiment is this measurement of the resistance, and or the Ohm's law, which tells us about this relationship, where the voltage across a voltage across a material, let us say this is your conductor and you apply some voltage across it, the voltage, the current, and you measure the current, apply the voltage, measure the current. So, there will be certain proportionality, V is proportional to, or the current is proportional to the voltage, and the proportionality constant is this resistance. Now, this resistance, it depends on the dimension of the material. Okay. So, resistance increases proportional to L, inversely proportional to the cross section area, and the constant of proportionality here is called resistivity. So, resistivity is an intrinsic property and it does not change with the dimension of the material, but if you change the material, then what you get is a different resistivity.
In which cases it will be R proportional to L and which cases R proportional to L by A?
No, it is R is proportional to L and R is proportional to inversely proportional to A. These two statements that you can directly write as R is proportional to L by A. So these three, statement 1, statement 2 and statement 3, these three mean the same thing. Okay, or this statement also means the same thing. If you take rho is a constant, so this also this implies R is proportional to L, R is inversely proportional to A. So 1, 2 and 3 and 4, these 4 statements are same. Okay. So another important relation is about the conductivity, which is nothing but the inverse of resistivity. Okay. Now what we are trying to do, we want to start with this known form of Ohm's law. So this is the form which you already know, and we want to frame it in a manner such that we will get to know something about the material property. So what we are doing now, we will replace R equal to rho L by A. So here V is equal to I times R, R can be written as rho L by A. Okay. And then what we did, we took this L to the left hand side, so V by L equals I by A, and instead of rho we put it as 1 by sigma. Okay. And V by L, what is V by L? You see, suppose if you have a conductor, this is a conductor and its length is L, So the potential difference, let us say here the potential is 0, here the potential is V. Corresponding to this potential difference, there is an electric field developed in that conductor, and that electric field, the strength of that electric field is given by V over L. Okay. So V over L is the electric field E, I over A is the, I by A is called the current density, the current passing through a surface area, through an area A, that is the current density, that is denoted as J, and we are writing as 1 by sigma, sigma is the conductivity. So J, this is the current density, is directly proportional to the electric field. Okay. This is another form of Ohm's law which is useful in determining this sigma. So, why we want to frame in this manner is because when we are trying to get the conductivity from the model, we will try to find from the model what is the current density, and from there we will compare what is the coefficient of what are the terms associated with the electric field, and then we will say that quantity is called sigma. So, we will see that shortly. So, this is just what we did here is just another form of Ohm's law. Then what we are going to do? Now we take the model, and from this model we are going to determine what the conductivity is. So, let us say that there is a charge E kept in an electric field of E, and how are we going to create this electric field E? So, we take a conductor of length L, apply some voltage around it, there will be electric field set up E is equal to V over L. Okay. So, we can set up this electric field, and there is an electronic charge in it, and in the presence of electric field E, the force experienced by the electron, the magnitude of that force will be the charge times the electric field. Okay. Now, force is equal to E times E. Now, you can apply Newton's law. So, m dV by dt is equal to E over E. Now, if you just go by this term, what it will say that okay, this is a constant, right? Mass of electron is a constant, the charge of electron is a constant, and E is what you are applying. So, this should mean that this velocity should keep on increasing and increasing with time. So, if you just integrate this, V is equal to E over m t plus some constant. So, it should increase with time, but that is not the case. So, and if the velocity is increasing with time, then the current should also keep increasing, but that is not the case in actual conductors. If you apply a voltage, then the current is usually a constant. So, that means the electron will accelerate up to some point of time, and then it will attain a steady state. So, that means there has to be a resistive term. So, this is the accelerating term which is applied by the this potential difference, the source of which is a battery. There should be something, a resistive term, and that resistive term should increase with increase in the velocity, so that at a particular velocity it should the electron should no more accelerate, the force should become 0. So, there should be a velocity dependent resistive term in this, so that the current does not increase infinitely. So, we call that resistive term as
E by m t plus what is that?
this is some integration constant. If you just integrate this, so this is some arbitrary constant. You don't some.
You are on mute.
Yeah, constant of integration. Is that fine? Okay. Now we'll go ahead. Now we added that resistive term, negative resistive term. Why? Because that will not allow the current to increase infinitely. Okay. Now what will happen? Now we try to see the steady state. At steady state means the electron will start increase, the electron will start accelerating due to this term. It will accelerate, and when it will start getting some acceleration, then the velocity will increase, and when the velocity will start increasing, then this term will come into play, and this term will slow down the electron. So, there will be a certain velocity at which this term will be equal to this term, the resistive term, and at the steady state this quantity will become 0, or dV by dt will become 0, there will be no more acceleration. At that point of time, you can calculate 0 is equal to this, and from here you can get what is this coefficient gamma. Okay. So, gamma you now substitute back into this equation, and m dV by dt is equal to, now we have substituted for gamma, and if you take this E times E common, what you have is this expression. Then you integrate at time t equal to 0, let us say the velocity of electron is 0, and time t equal to t, the velocity is v. When you integrate, what you get finally is just a second. Am I still audible, right? I think.
Yeah, you are able to, I'm able to hear you.
Yeah.
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 So
So
now,
now,
okay. So now what we have is, so when we do carry out this integration,
Can't see your screen, sir.
what?
Can't see your screen.
You cannot say. Okay, okay. I think I need to share. Okay.
Can we go to the previous page, sir? Actually, towards that end, we lost.
Here.
Yeah. What is this EE?
So,
PSP?
so electron E is placed in the electric field E. Okay. So
No, sir.
an electron E.
EE by E plus C. Yeah.
Yeah. Okay. You. I'll tell you what this is. So you just try to integrate this. Okay. dV is equal
So I
to.
understood that point.
Yeah.
I understood that.
Yeah. You just.
Here, V equal to EE by M T plus C, is it?
Yeah. Plus this is some arbitrary constant. You need not care about this.
Ah, okay.
Okay. So then what we have here in the next is we added a resistive term here, and we tried to find out what is the steady state velocity. So at the steady state, let the velocity be Vf. This Vf, it denotes what is the velocity at which both the accelerating and the resistive term become same. So we expressed gamma in terms of EE over Vf and substituted here, and what we have is this expression. Then we can carry out the integration, and on carrying out the integration, what we have is this final expression, this one. Okay. So what this means is that as t will go to infinity, v will tend to this steady state velocity, and from here there is one important step here at when you carry out this integration from here to here. This t, see here there is, see logarithm, it has no dimension, and this side is also dimensionless, and if this has a dimension of time, this should have a dimension of 1 over time, right? So this t, so this is 1 over time, 1 by tau, and that tau we can substitute as this m Vf E over E. This tau is called relaxation time, or the mean free time between the collisions. Okay, and it depends on, what does it depend on? It depends on the mass, the steady state velocity, what is the charge of electron, and the electric field that you are applying. For an electron, this mass is a constant, right? Mass is 9.1 into 10 to the power minus 31 kg. This E is a constant. E is 1.6 into 10 to the power minus 19 coulomb. This electric field E, this you can control experimentally, and this velocity, this final velocity or the steady state velocity is directly related to this tau, or the mean free collision time. Okay. So with this in mind, we will go ahead. So we told that from this model we want to put it, our overall idea is to frame the Ohm's law in this form, J is equal to sigma A. So now let us look what do we have for the charge current. For the charge current, let us say there are NF electrons in the sample or in the material per unit volume. Okay, NF electrons per unit. That means NF is the number density. So this you remember, this is the current flowing per unit area, right? So NF E times Vd. So what is this? NF is the number density, number of electrons per unit volume. So NF is equal to, you can say, number of electrons per unit volume times, what is this Vd? Vd is the distance per unit time, the distance along x per unit time, and E is the electronic charge. Okay. So this is what N is the number of electrons times the electronic charge, that is your current. So N E over T is the current, right? You are getting it. And this volume V, it can be written as the distance times the cross section area. So this distance cancels and this is I over A. So this is basically I over A, and J can be written as NF E times Vd. I hope this expression is clear. NF is the number density.
N by T, E is nothing but I, is it?
No, I is nothing but N number of electrons. So this is, okay, current is equal to Q by T, right? Where Q is the charge. Charge is number of electrons times electronic charge, a single electronic charge, and T is the time. You got this point?
Yeah.
So N by T I substituted this as I. So here the main point to note is that J is equal to NF E times Vd. This Vd is the drift current in the material. Okay. And this Vd, what we are writing? We are writing it as E tau over m. So okay, where we got this V? This V is actually this E tau by m. Oh, here we have written Vf. It is the same thing here. So Vd is actually Vf here. It is actually Vf. So Vf is equal to E tau over m, that we got from here. Okay, the final velocity here. And it is okay. So these quantities are the averaged quantities. Okay. So what we are happening is, suppose if we have this collisions. So there are quite a number of collisions. So there is this lattice, right? Suppose one electron collided with another electron and it is now at zero velocity on average, and it got accelerated by this accelerating term, what E tau. So E over m, this is the acceleration. It got accelerated till time tau. It is the mean free time between the collisions. In between that there is no other collision. Okay. So there will be a yeah. So acceleration times this mean free time is, this is your average final velocity of the electrons, that we are substituting here. E tau over m. This point you got. This we are trying to substitute over here. On substituting that, what we get is NF E square E tau over m. So we are just substituting for this V here. Vd we have put it here. Okay. So here what we got is NF E square tau E over m. You got this point?
Yeah.
Yeah. So now what?
Vd is what, sir? Vd. What do you call Vd and Vf? What is it?
Okay. So this Vf. See, what is this Vf? Vf is the velocity at which the electrons will start. Suppose this is a material. The electrons on an average they will start accelerating, but they will get retarded by this resistive force, right? Then the steady state velocity, or the drift velocity, the average drift velocity with the velocity the electrons would be moving, that is called this Vf. This is the steady state velocity, right? And what is this Vd? Okay. So this is like between two different collision. So one electron is here. Between two collisions, there would be no resistive term. It will just accelerate, keep accelerating till it hits the another collision. Got it right? During that time interval tau, the motion of the electron is only pure acceleration. You got the difference, right?
Yeah. So it's basically based on the motion of electrons.
Yeah. So this is an accelerated. So this is the final velocity. You might have v equal to u plus at. This is accelerated velocity. Okay. After acceleration, in the time tau, there is no other collision, and there what you get is this acceleration times tau. So this is the final average velocity of the particle. And what is this? This is the steady state velocity, Vf. That does that make sense? Or you can just it is nothing but it is simply this only. Vf is equal to, from this expression you understood, right? From here,
Yeah.
Vf is equal to, what is Vf? E tau by E tau over m. Basically, these two are the same thing. If you see it, this expression,
Yeah. It's just yeah.
got it right? What is this Vf?
Yes.
Yeah.
Just rearranged, right?
Yeah. So on rearranging, so you got to know that this steady state velocity and the average final velocity, these are the same thing. Just that conceptually there is a bit of difference, but from mathematical expression you saw that this both are same, right? This is E tau by
Steady state
n.
velocity and average.
Yeah, so these are basically the same. So the point here to note is that this can be thought of as it got accelerated in that particular time tau, and there was no collision in between. So basically we are just substituting from this. If you are like confused about this part, then you can just forget it. You just substitute Vf from here, that we substituted here, and Vf, there should not be any confusion. Vf is equal to this, okay, that we substituted here, and what we got is this, J is equal to Nf E square tau E over m. This is clear? Yeah. Now what we wanted to study was what is the conductivity. So we have got a form, you see, we have got a form in which J is directly proportional to the electric field E, and there is a certain factor associated with E, right? Now we can compare this with the Ohm's law. So remember that this we get from the model, and this we are getting from this is the Ohm's law. Ohm's law in terms of conductivity. So now we can compare that sigma is equal to, sigma is nothing but your this term which is behind E. So sigma, it turns out to be Nf, which is the number density of electrons in the material, E square tau over m. So Nf is the material property, it is the number density of electrons in a particular material. So for different material we will have different number density of electrons. E is a constant, m is a constant. What is this tau? This tau is coming from, this is an input to the model, input of the Drude-Lorentz model, okay. So once we have an estimate of tau, we know what is the conductivity in the framework of Drude-Lorentz model for a given material, okay. This point is clear, right? Okay. Now For a certain material, typically in a metal, for example silver, the number of electrons per unit volume is of the order of 10 to the power 28 electrons per meter cube. Electronic charge is a constant. The mean free time tau, it is of the order of 10 to the power minus 14 seconds. And the mass of the electron is 9.1, which is a constant, 9.1 into 10 to the power minus 31 kg, it is a constant. If you put all this in this expression, you get a numerical value which is sigma is equal to 3 into 10 to the power 6 ohm per meter, which is nothing but electrical conductivity of a typical metal. So this is one of the success of the Drude-Lorentz model, that it can explain what is the electrical conductivity of the material. So if someone asks you what is the conductivity or calculate the conductivity in the framework of Drude-Lorentz model, the working formula is this: sigma is equal to Nf E square tau over m. Okay. So this is about the electrical conductivity in the framework of Drude-Lorentz model. Now we will go to see what is the thermal conductivity. Okay. Now thermal conduction is a method of heat transfer. So let us first define what is the scope of materials that we are considering, that we are studying here right now. So there are different modes of heat transfer like conduction, convection and radiation. What is conduction? For conduction to happen, there should be a physical contact between the solid materials. And convection, and it mostly happens within a solid. What is convection? Convection means it particularly refers to fluid systems, which generally include liquids or gases. Okay. So here what happens, the bulk of the material, a certain region of the material will actually move. So physical transfer of heat will take place from one region to the other because of currents in the fluid. That is your convection. Okay. In some engineering applications, what they do is they use a blower or they use some certain agitator. So we agitate a liquid so that it will mix by means of the convection. So what will happen is, for example, in this natural convection process, what happens, we heat it from below. So this region will get lower, the density of this region will reduce, they will rise up, and the heavy fluid from the top, it will come down. So this current is called convective currents, the current set up in this way. And because of this actual motion of the particles, the heat is getting mixed or heat is getting transferred. And the third part is the radiation. It is another method of heat transfer for which you don't need any medium, and these are carried by certain waves called electromagnetic waves. These are like for example the light, the infrared waves. These are different frequencies of electromagnetic waves, and for example from sun to earth, the heat that will come is by means of this radiation. Okay. Now there is this concept, for example, if we are sending a satellite, in a satellite where in a satellite surrounding a satellite there would be no atmosphere. So the region which will be facing towards the sun, it will be so much of heat, it will be receiving so much of heat by radiation that the temperature difference in the side which is facing towards the sun is quite different from the side which is away from the sun. Like for example, in moon, it doesn't have an atmosphere. There is a very high change in the temperature. Like during the daytime, it will be very, very hot, and during the night time, it will be very, very cold. Whereas because of this convective currents, like for example in earth, so the atmosphere, because of the convection, there is less difference between the side which is facing the sun and which is facing away from sun. So this is like one of the application where this convective processes is moderating our climate. Okay, but for the present scope, we will focus only on the conduction, because most of the materials that we will be using for engineering from the engineering perspective, that will be that will be conducting in form of like solids. Like in most of the materials, in most of the metals, the carriers of the heat are the free electrons. So, nevertheless, insulators also conduct heat, but they conduct heat by vibration of the atoms which are constituting them, and this vibration of atoms, these are called phonons. Okay. So, this vibration of atoms are called phonons. The insulators, they can also conduct, but they do not have free electrons. So, how will they conduct? By means of this thermal vibration of the constituent atoms. So, now let us look at the definition of this thermal conductivity. The thermal conductivity kappa is defined as the heat transferred per unit time per unit area per unit temperature gradient. So, temperature gradient is what? So, delta T over delta X. Okay. And the heat current, so amount of heat passing per unit time per unit area is this J, it is denoted as JQ, and if you rearrange this, what you get is JQ is equal to minus kappa times dt by dx, and this K is your thermal conductivity. So, in the framework of Drude-Lorentz model, we are trying to derive what is the thermal conductivity. So, let us consider a metal and we try to look at a particular position x. So, thermal conductivity means was what? We want to know what is the amount of heat Q which is getting transferred from this hot end to the cold end, right. So, and this energy is exchanged by means of electron collisions. Okay. So, these are exchanged by means of collisions. Now, how are we going to go about it? So, we will look at the energy of the electrons. The energy of the electrons is a function of temperature, and the temperature is a function of the position. For example, this is the hot end and this is the cold end, and there will be a temperature gradient over it. So, this will be at higher temperature, this will still at lower, and it will come to this end. So, the temperature is a function of the position. Okay. So, overall the energy is a function of temperature, which is a function of the position. So, now let us try to look at microscopically what is happening at this interface. So, what we are trying to see at this interface x, at this interface located at x, what is the amount of, so you see the electrons are moving randomly, right. So, let me try to make it. So, we are trying to look at x. So, there are certain amount of electrons which are moving randomly in a very random fashion. Half of the electrons, so and the number density is NF, right. So, half of these electrons, so there is the probability that half of them is going from the hot end to the cold end, and there is half probability thus that the electrons are going from the cold end to the hot end. So, NF by 2 electrons are going this way and NF by 2 electrons are going this way. Okay. And before going this way, what is the time or what is the position where they would have met their last collision? That would be in a time interval of tau. So, it is x minus v tau where they have collided last from the hot end. So, this will have some more energy, and for the electrons which are coming from this side, they would have their last collision at the position x plus v tau. Okay. So, the last collision, let us try to look for those electrons which are coming from hot to the cold end. For those electrons, the last collision has happened at x minus v tau, and the energy at that position is E, which is a function of the temperature, and it is a function of this position x minus v tau, and it is NF by 2 electrons which are moving in this x direction. So, the heat current from the hot to cold region is NF by 2, because NF by 2 regions are going towards hot to cold. V is the velocity of the electrons times what is the energy they are carrying. And similarly, for the other from those electrons which are coming from the cold to hot region, it is Nf by 2 VE, but now the position is at x plus V tau. It is coming from here to here. Now the net transfer is what is coming from hot to cold minus cold to hot, and if you just substitute those expressions, it will be this. Now what we are going to do, we are doing some kind of a kind of approximation of linearity. So this is the linear expansion. So energy at position x minus V tau is energy at position x minus
minus V. Why is it compared to cold to hot?
Cold to hot? Yeah, see.
No, hot.
Hot to cold. What is your doubt?
Hot minus V tau, whereas cold to hot is plus V tau.
Okay, why is that? Okay, see, there are half electrons which are coming from hot to cold like this, and from cold to hot they are going like this, right? So Nf by 2 electrons are going from hot to cold in this direction, and Nf by 2 electrons are going from cold to hot in this direction. Yeah. So the net transfer of energy is energy carried by so I want to find what is the net transfer of energy from hot to cold. Okay. So energy transfer from hot to cold will be given by energy transferred by this set of electrons that will add to that energy from hot to cold, and this cold to hot that we have to subtract it out. You got it right? It is like, huh?
That's the net.
Yeah,
The net.
yeah. The net amount of heat which is going from hot to cold is, this is from hot to cold, is hot to cold minus cold to hot.
No, but what my question is, for hot to cold it is x minus Vt.
Okay, okay, yeah, okay, yeah. So say here, for those electrons which are carrying heat to x, they would have they are coming from cold region, right? The cold region, it will be towards the colder side, which is at V tau distance towards the colder region.
Yeah.
So it is the energy at this particular position which is carried to here. You got it? The energy, so this set of electrons, Nf by 2 electrons are carrying energy from this position x plus V tau to x.
Okay, so the V tau is our distance. Okay, got it. Okay.
V tau is the distance, this distance.
Got it.
Okay. Okay, so now this is just a Fourier this is a Taylor expansion. Okay. Similarly, E T x plus V tau, that you can Taylor expand and write it as like this. And when you substitute these two, what you get is Nf V by 2, and you just put it. And when you simplify this, the term that you get is this. Now you see this dE by dx, this term we can write it as, so E is a function of temperature, right? So dE by dt and dt by dx, this is just the chain rule that we have applied. Okay, and this dE by dt, what is this? This is your heat capacity, which is like CVE. Okay, or this is your electronic specific heat capacity. So that we have substituted here, and what we have is this V square tau CVE dt over dx.
Electron specific heat capacity.
Yeah, because what we are saying is that the heat capacity can be due to like ion movement, also other movements. What we are specifically considering is what is the heat capacity only due to the electrons.
Yeah.
Right. Okay. Now we have this expression. Now we are, so this is the expression that we had. What we are going to do is, if we take, so this was, the velocity was taken only in the x direction, right? But so this is actually the velocity in the x direction, but v square is vx square plus vy square plus vz square. This you understand, right? Because the velocity is, the square of velocity is the square of components, all these components.
Yeah.
Right. So, and now since we are assuming that what is the probability if you try to take the average v square is what? So, vx square, the average velocity in the x direction plus average velocity in the y direction plus average velocity in the z direction, and there is no reason to there is no reason that why the velocity in the y will travel more than the velocity along x. I mean, basically it is isotropic.
Yeah.
Right. So, vy square plus vz square. So, what we will write is 3vx square. Okay. So, vx square is nothing but 1 by 3 v square. Now, this v square is the actual speed of the, this is the speed, not any component. Earlier, this was one component along x, it is 1 by 3 times the v square, which is the actual velocity, right? Or the v is, you can think of it as the speed. So, that is why this 1 by 3 term comes in. So, 1 by 3 v square. So, here what we did was this was vx. So, 1 by 3 v square average tau c v e dt by dx. Now, this we already had seen. This is the Fourier's law, and this we got from the Drude-Lorentz model. So, just like earlier, for electrical case, this was Ohm's law and this was from Drude-Lorentz model, and then we compared the quantities, right? So, here this is Fourier's law of heat conduction. From there we get this thermal coefficient of thermal conductivity, that kappa, and we compare it with the Drude-Lorentz model, and whatever we get here, that we will say it is kappa, or this is that coefficient of thermal conductivity, right?
Yeah.
Yeah. So, this is the expression, and it has the units of watt per meter per Kelvin, and typically in a particular material, this v square is of the order of 10 to the power 10 meter square per second square, tau is of the order of 10 to the power minus 14 second, and the electron specific heat is 10 to the power 6 joule per meter cube per Kelvin, and for which is actually the order of magnitude is around, and if you put all this in this expression, what you get is this value. Kappa is equal to around 100 joule per second per meter per Kelvin, which is of the same order of magnitude for metallic conductors. So, the thermal conductivity also, it is also explained very well by the Drude-Lorentz model. Okay. So, we could explain the electrical conductivity, the thermal conductivity, and there is another very important success.
These values in the previous slide, sir, values v square,
Yeah.
10 power 10 meters per second.
Yeah.
Meter square per second square, is it? Meter per second, yeah, okay, got it.
It is
Yeah,
v
so,
square.
where is 10 coming from?
Yeah, that is coming from certain calculation that we'll see in a while.
Okay.
We will get to know, like we'll see how can we calculate all this. But
So
for
the
now,
CV or specific it also,
Yeah.
you are putting this value. It is basically you are doing a calculation, is it?
yeah, so that comes from a calculation that we'll see in a while, how we are getting all these quantities. So now what we are going to see, we saw that it can explain the thermal conductivity, the electrical conductivity. Now what we are going to see, how, so it should, now we have built a model. So the point till now is we have a model called Drude-Lorentz model, it can explain what is the it can explain what is the thermal conductivity, what is the uh, electrical conductivity, can it make some predictions or not, and if yes, how valid they are. Now this we are going to try to see. So we saw what is the electronic conductivity in the framework of Drude-Lorentz model, which is this, and the thermal conductivity this. And there was this general observation that a good thermal conductor are good electrical conductors. And this statement has been systematically studied by Weidemann and Franz, and they gave an experimental relation that the ratio of thermal conductivity over the electrical conductivity, it is directly proportional to the temperature, or if you assume a proportionality constant, so kappa by sigma t will be a constant, and that constant is around this value. And for most of the materials, it is of the order of 10 to the power minus 8 into this 2.4. So this is the Weidemann-Franz law. Kappa by sigma t is your constant, is the constant. Now let us see from the framework of Drude-Lorentz model, can we find what is this value. So what we have to do, we just have to substitute these expressions and check. So let us just check kappa over sigma t, is it a constant or not. So we substitute the expression for kappa, we substitute the expression for sigma. So this is your k, and this is your nf, this is your sigma. Then what we did, this mass, this came up, we did some rearrangement. For CVE, what we can put is, CVE we can put 3 by 2 NF kb. This is, so this is this is how we can calculate the electronic specific heat in the framework of kinetic theory, and from there we can get this value. What this value? This CVE. Okay, here this value that we can get it from here, and this is in the framework of kinetic theory of gas. And another important result from kinetic theory of gas is that half mv square is 3 by 2 kT. Okay. So here mv square, you see this value, right? This we can replace it from here, and this Cv we can replace 3 by 2 NF kb. This we are putting it here. Okay. And on substituting, what we will get? On substituting, we will get this expression, and here this t will cancel this t, NF cancels NF. So we will be left with 3 by 2 kb square E square. So we are left with this expression. You see, the Weidemann-Franz law, it says that the thermal this ratio, this has to be a constant, which is actually a constant here. 3 by 2 kb is the Boltzmann constant, E is the charge of electron, which is a constant, and the order of magnitude, you see, it came out to be 10 to the power minus 8, which is a constant, and it is somewhat same as the see, it is also 10 to the power minus 8 the order of magnitude, and here also it is 10 to the power minus 8 order of magnitude. So that is why it is a when this thing was predicted by the Drude model, it is one of the greatest success of the model. Okay, experimentally we saw this, and from the model we get this. So what we can explain, the thermal conductivity is successful. This is the success of the Drude-Lorentz model, the electrical conductivity as well as the relationship between these two conductivities, which is the Weidemann-Franz law. But there is a sort of happy accident. So when we carefully look at the value of kappa or the thermal conductivity, this was matching very nicely with the experiment. But if you look at it very carefully, then this is the result of a very happy accident. There are two terms here, you see V square term, and there is this electronic specific heat term. These two are actually wrong in the framework of Drude-Lorentz model. So what happened was this CV, or the electron specific heat, it is overestimated by a factor of 100. So whatever the actual value is there in the framework of Drude-Lorentz model, it is 100 times more. So what did we see? CV, this was what? This was 3 by 2 NF kb. But in reality, it is 100 times less than this. The electron specific heat is 100 times less than this particular value. And this average velocity is 100 times more than the value. So in Drude-Lorentz model, this V square is underestimated by a factor of 100. Okay. But since this both are multiplied and this is underestimated by 100 and this is overestimated by 100. So two wrong quantities, when they are multiplied, the wrong factors they got cancelled out, and what we get is the actual value. So it is a kind of a happy accident. But when we look closely, the specific heat is overestimated and the average square velocity is underestimated. And another important failure of the Drude model is that, so there is something called Hall coefficient, okay, and Hall coefficient you need not know like exactly what it means right now, but you can just keep in mind that RH is positive if the charge carrier is positive, for example the electrons, and this Hall coefficient is negative. Okay, Hall coefficient is negative if the charge carrier is negative, and the Hall coefficient is positive if the charge carrier is positive, for example the holes of a semiconductor. Okay, and the Drude model only predicts that RH is negative for only negatively charged carriers. It does not say why RH can be positive, and it has a very big numerical mismatch also, which is why
What is RH?
what
Hall coefficient. Oh, okay.
yeah, Hall coefficient. Hall coefficient do not match. We do not get exact value of Hall coefficient from Drude-Lorentz model. That's all you can remember for now. And another important factor is we are just calculating here the input of sigma is what? NF is square tau over m. NF is the electron density. So we are just considering the number density of the electrons, and we are not bothering in which direction the electron is moving. So the isotropy or anisotropy, that we are not taking into consideration, but in reality the isotropy also plays a role in which direction what should be the conductivity. Okay. So that can be that has been explained later, but in the framework of Drude-Lorentz model it cannot be explained. So these are your failures of the Drude-Lorentz model, and if we want to see why this Drude-Lorentz model has issues, because what we actually did was, this is just a recap. So this is your thermal electrical conductivity, thermal conductivity, and these two are the results of ideal gas.
Yes.
What we basically told in the entire argument is that we took the results of ideal gas, we say that electron is also behaving like an ideal gas, and imposed the rules of ideal gas onto the electrons. That is the crucial factor why that is the crucial factor why there is a failure of the Drude-Lorentz model in many of these major aspects. Okay. So now let us look what is the so as I had told, this CV was over predicted and this V square was under predicted. Now let us try to see how we can get the so in the lecture, if you go through, the professor has taken an example of the silver metal, and the measured conductivity is this sigma, and for a 1 meter wire and diameter 1 mm, what will be the resistivity? So resistivity, it can be just calculated, resistance can be calculated as rho L by A. All the values are given, sigma is given, length is given, diameter is given, and if you calculate, you will get 0.02 ohm. Okay. and if you put 1 volt across the wire, what you will get is 50 amperes of current if you put this resistance. Okay. Now, what we are going to, what we are trying to see is what should be the value of tau, so that it will match the resistance of the silver. Okay. So, here we are trying to estimate what is the value of tau. Okay. Now, we will try to find what is the amount of electronic charge which is passing per unit time. So, the charge is, so current is charge by time and charge is current into time, and let us say that the drift velocity of electron is Vf and the time taken to, so we are taking this as the system, right, and length is L. Let us say that the time taken by the electron to travel distance L, that is L over Vf, this is the time taken. Okay. So, the charge which is getting carried is I times time, time is L over Vf, and that is nothing but N, the number density of electrons times the cross section area, and L is this length L E. You remember this, right? J is equal to N V A. So, and so this was the expression we saw a few minutes before, and this was I over A.
Yeah.
So, this I we are just writing as NF A V E. Okay, and so this is the same expression. If you see, if L cancels, I is equal to, or I hope this is clear. From here, what you can, I is equal to NF V E A, right? This part is clear, right? And from here, what you get is V is equal to I over NF EA. Okay, this is the same expression. We know the current, we know the number density of silver, we know the electronic charge, and we know the cross section area. Okay. From there, we can calculate at what is the velocity the electron is drifting. You got it, this part?
Yeah. Yeah.
Yeah. So, V is equal to, these are the measurable quantities, NF is the number density, electronic charge, area. From here, we got that it moves around 6 into 10 to the power minus 3 meter per second, around 6 mm per second, and if you just put, this is meter per second, which is around 6 mm per second, and from here you will get the value of tau. Tau, you remember, this is the formula we saw very early. It is M E E or V F. V F we substitute from here. M is the mass of electron, 9.1 into 10 to the power minus 31. E is the electronic charge, 1.6 into 10 to the power minus 19. And this electric field E, that we are saying that we are across a length of 1 meter, we are applying a voltage of 1 volt. So, electric field is V over L, which is 1 unit of 1 SI unit. And if you substitute all this, what we get is 3.5 into 10 to the power minus 14 second. So, tau is of the order of 10 to the power minus 14 seconds. So, this is how you calculate tau. Got it right? Like if you can be given, so important formula to remember is this, or if you remember this, J is equal to NF VE, that is equal to I by A. From there you can calculate what is the V. From these are all measurable quantities in the experiment. This V is you are inferring microscopically, you are not actually like looking through a speedometer or something. This you are measuring from these quantities, and from here you can indirectly calculate what is tau. That is all. So, here keep in mind that the mass of electron is 9.1 into 10 to the power minus 31 kg. 31 kg. If someone will ask you what would have been the case if some other species if I had used, then you have to change the mass, okay, that you just have to keep in mind. So
If
this
it is
is
a
an
proton,
important,
it changes.
huh?
Proton or a, if it is a proton or a hole, it changes.
Yeah, for a proton or hole it will change, the tau value will change. Okay, now okay, so this is the value of tau that we are getting. So and this is related to why there was a failure of, why was there a failure of the Drude-Lorentz model. That is because this was 3 by 2 NFKB, which is actually 100 times more than the actual CV. Actual CV. Okay, and V square is 100, around 100 times less than actual V square. Okay, and why this happened? Why this happened? Because the model that was used was the model is using kinetic theory of gases. The Drude-Lorentz model is using kinetic theory of gas, and in kinetic theory there is a particular assumption about the velocity distribution of the particles, and the particles are assumed to be non-interacting ideal gas molecules, and the distribution of velocity is called Maxwell-Boltzmann distribution. Okay, from Maxwell-Boltzmann distribution you can actually calculate what is V square. From this distribution it looks like, what it Maxwell-Boltzmann distribution, it looks like this. Okay, it means that there is a certain velocity at which the particles are moving at the highest speed. At very high speed there are less particles, at very low speed there are less particles. Okay, so that you need not go through right now. For you to understand, only you can just understand that the velocity distribution used for in the Drude-Lorentz model was Maxwell-Boltzmann, which is for a classical particle, whereas electrons are not classical particles. So and they follow a different velocity distribution called the Fermi-Dirac distribution. So that is a completely different distribution which takes into account quantum effects, and that is why we see this discrepancy. So that's all for you to understand in this lectures, and in the future lectures they will sir will talk about particularly from Maxwell-Boltzmann distribution what is the, so we'll go more into this distributions and all. Now we can have a discussion on the questions related to this. So what do you think the resistance of a conductor? So what is the resistance of a conductor? R is equal to rho L over A. Rho is resistivity, which is an intrinsic property. R is an extrinsic property. It depends on the dimension of the conductor. So what do you think would be the correct answer?
It's a constant depending of its independent of, no, increases with increase in length. No, decreases with increase in length.
It decreases with increasing in this one, right? What about this statement? Decreases with increase in cross sectional area. So
both 1 and 2.
Okay, 1 is correct because R is inversely proportional to A. If this increase, this will decrease. Decreases with increases.
No, not that. Fourth is correct. Sorry.
Fourth is correct. Yeah, increases with increase in length. Okay, is a constant independent of length. Okay, this is wrong. And okay, cool. What about this conductivity of? So remember, this is conductivity. What is conductivity? Sigma is 1 by rho. Now you can tell me this. What will happen? Will the conductivity
increases resistivity 1 by resistivity? So resistivity decreases with presence of velocity.
So what you have to think of it as, you imagine a cube of a certain dimension, you just certain dimension of the material. So once you are fixed with this dimension, now you can think. Now if you alloy this volume of material with if you alloy it and take this volume of material, will the conductivity increase?
There is resistance, right?
This is
Then it
conductivity.
should, yeah, no, with the alloying element, the resistance should increase, right?
Yeah, we actually cannot say because it depends on. So we cannot say for sure that it will increase or decrease. It depends on the type of the material which you are alloying with. If you are using a better conductor, then it will increase. If poor conductor, then it will not increase. So anything can happen. So you cannot say it will increase for sure. So in presence
Grain
of,
boundaries will,
yeah,
grain boundaries will,
in presence of grain boundaries, what will happen?
it will increase, right? It will start to
Say, imagine that this
interact.
is your material and there are grain boundaries. So grain boundaries is, these are the regions which will not allow, so there will be a mismatch of lattice. So the electron will be going freely and it will suddenly see, oh, there is a boundary here. So
Okay, it restricts it, decreases it.
so it decreases with presence of grain boundaries. So this is wrong. And what about the
Amount
third?
of porosity, that is
Porosity,
true.
yeah, it
Yeah, it will decrease.
decreases, correct. And in presence of precipitates,
This is
precipitates means some
true.
impurity, you can think of it like this, like this.
Yes, true.
This is true. Yeah, correct. These two are the correct answers. What about the third? So this is a conductor. So you first you have to write V is equal to IR. R is rho L by A or I times 1 by sigma L by A. Now what you can infer about this?
Uh, so anyway, the current gradually, the conductor is gradually increased.
Yeah,
So current gradually, I
increases.
will be coming back.
This is correct or not?
No, decreases. Current will
Voltage,
gradually decrease.
see, voltage is increased.
Ah, okay. Voltage applied across a conductor is gradually increased. Okay, yeah. Then it is increases. Correct.
Yeah, the current is actually increasing. The resistance, what will happen to the
Resistance,
resistance?
the current is increasing, resistance will decrease, but it is proportional. If I take I as a constant, then R is also increasing.
See, you cannot infer from here. See, for a given material of a given dimension, R is constant.
Yeah.
So, whatever be the voltage, it will not change the material, right?
Yes.
Neither
Not
it
change.
will change the dimension of the material in principle. So, R you have to infer it from the material property. The material property is resistivity and its dimensions L and A. Okay. So, and what
So
Ohm's
it
law
will.
say? Ohm's law doesn't say anything about the resistance. It says about given a conductor, the V is proportional to I, and V is and the proportionality constant is called resistance. You got that point?
Yes, got it. Yeah.
So, what will is this statement correct or wrong?
It's not correct.
Yeah,
Power consumed increases. Correct.
yeah. Why? Because power is,
Proportional to IB,
yeah,
I square R.
yeah. Proportional is I square R. I increases because voltage increase. So and or it is V square by R. R is a constant, so it increases. The power consumed increases. What about the electric field? It will decrease, or you remember this formula, right? What was the relation between V and the electric field? Electric field
Is
is
E by L.
V by L. Yeah. Now,
E by
if the voltage will increase, then electric field will
electric increase.
increase. So this statement is wrong. Okay. What about this fourth one?
In an infinite metal wire, if two free electrons are 1 meter apart and the wire is subject to an electric field E, both electrons initially accelerate. It is possible that the electrons can move.
Yeah. So this is an electron, this is an electron, and they are 1 meter apart.
Meet is correct. Both electrons will actually initiate is correct. Accelerate, initially
Yeah,
accelerate is
yeah,
correct.
correct.
That is behind, they can meet also is correct, right? Electrons cannot
Yeah,
meet.
because these electrons are moving randomly actually. These are
Yeah,
moving
they can
random.
interact.
They can meet sometime. This is correct.
Yes. Electron that is behind will accelerate. No, that is not true. We do not know that.
Yeah, because the
Two
electric
electrons.
field, what we are, it is subjected to electric field E. So the
Yes.
entire conductor is at the electric field E.
Yeah.
Okay, this I mean here also there will be electric field E. Here also there will be electric field E. So the force on it will be the same. So this statement is wrong. Okay, the two
Last
elect,
also is wrong.
huh?
That is also wrong. Two electrons will prevent each other from moving is also wrong.
Yeah, because here in the at least in the framework of Drude-Lorentz model, we are saying that electron they are not interacting, they are not talking to each other.
Yes.
Yeah, correct. What about this? In a metallic conductor at room temperature,
At room temperature, in the presence of an applied field, the average velocity of electrons is zero. With the applied field, there will be some velocity of electrons. Uh, the instantaneous velocity of all electrons is zero. The average velocity of electrons is not zero. That is correct. The average speed of electrons is not zero. That is also correct. The last two is correct.
uh, you mean this and this?
Yeah.
See, you know the difference between velocity and speed, right?
Yes.
Yeah,
Velocity
velocity
is
is
one
a
direction.
vector and speed is this Vx square plus Vy square plus Vz square root under. Huh? Now see, in a metallic conductor at room temperature in the presence of an applied field, average velocity is 0. This is wrong. Okay, correct? Because there will be some drift. Okay.
Yes. There will be some movement. Yeah.
Yeah, that is E tau over m. This is the steady state. Okay. And instantaneous velocity of all electrons is 0. This is wrong, correct? The average velocity is not 0, correct? Average speed is not 0. Okay, correct. Okay, what about this? Atomic vibrations are in all the metals at room temperature. What is the primary mode of heat transfer in the metals?
It's in the metal. It is conductivity.
I mean, what is the source of that conductivity?
Basically through electrons.
Yeah, through free electrons. That's what we learned in the
Free electrons.
Drude-Lorentz.
Yes.
Free electrons. So it is false.
Atomic vibration is only phonons, right? That
Yeah,
is
those are the
mainly conductive.
phonons. Yeah, phonons are also there in certain crystals and certain materials. Phonons are the main conductor, particularly in insulators. The phonon is the
Yeah.
main mode of heat transfer. Okay, what about this? A force experienced by an
Force.
electron within a solid under the external field. So you remember this, right? Force is equal to m dv by dt is E minus gamma times velocity. So it is under an external field. So when we put this is a conductor, there is an electron, and external field how we are applying by a voltage. Okay, it is the sum of two terms.
Yep.
So what are these two terms? This is an, okay, you can tell what is the correct one.
E E. E.
Which of these option will be correct?
Positive acceleration force and so that is positive acceleration force plus
Yeah.
what is this? Is no
Say,
resistive force or negative force?
yeah,
Negative resistive
this
force.
is negative, right? It is slowing down the
Yeah.
electrons. So it is negative resistive force. So
Here rho is our resistance, right? Resistivity.
yeah. So you see this gamma was related to what? E over Vf, and Vf is related to tau You remember Vf was related to tau and tau is related to the resistivity or conductivity. This is 1 by rho equal to Nf E square tau over m. Okay, this tau is related to nothing but your this velocity Vf. Vf equal to E tau over m. Okay, so basically this is a resistive term. Okay. Okay, so what about this electrical conductivity of a trivalent metal having atomic number 13? Okay, so this I will. Okay, so how do you go about it? Atomic number 13, a trivalent metal. So it is already saying it is trivalent metal. When it says atomic number 13, it refers to aluminum. If you look in the periodic table, okay.
Yeah.
Pe-
So it is 2 plus 8 plus 3.
2 plus
It is
8
3
plus.
ways.
Yeah, so it has, so what we want to find here is the number. So what we want, electrical conductivity we want. So let us see how we can proceed about this. We want to find sigma, that is what the question has asked, and what is the formula for that? It is Nf E square tau over m. We know what is m. M is 9.1 into 10 to the power minus 31 kg. Tau is of the order of 10 to the power minus 14 second. This we had seen a few time before, right? Some time before. It is of the order of 10 to the power minus 14 second.
Yes.
E is 1.6 into 10 to the power minus 19. All we need to find is Nf. So Nf is what? This is number of electrons per unit volume. How do we find this? We know the density of an aluminum is, density of aluminum is how much? If you just Google it out, it is
No, no. It's atomic number.
density of gallium, density of what is aluminum.
Mass.
Let me just Google it out. It is 2.7 gram per cm cube. 2.7 gram per cm cube, which is 2.7 gram, and 1 cm is 10 to the power minus 2 meter cube. That means it is 2.7 into 10 to the power, so this will come out to be 10 to the power 6 gram per meter cube. Okay, so that means 2.7, so it has an atomic mass of, if you look at the periodic table again, it has atomic mass of 27 atomic mass unit. So this much gram, 10 to the power 6 gram, will imply, if you just this many moles per meter cube. Okay, this point is clear, right?
Yes.
And this many moles means, in terms of numbers, 6.023 into 10 to the power 23, this many atoms per meter cube, and each atom will be giving 3 electrons, so we have to multiply with 3. Okay, if you just calculate this value out, what you will get? Nf is equal to, how much you get is
10 power 20 approximately. No, 10
20,
power
23 and 6 is there, so it is yeah, I think I have calculated it somewhere. Yeah, you get this value, 1.8 into 10 to the power 29 electrons per meter cube. Now you put the value of n here. E you know, what is the tau you know, m you know. You, after putting everything, the value that you will get is around 10 to the power 7.
Yeah, 10 power 7. But somehow I thought without the. Okay, maybe we have to do the right calculation without that.
Now here I had just calculated, you see, and I have taken 1.8 into,
So you wrote a Python code for it. Huh?
yeah, it is just like few lines of code. Yeah, so sigma is n square tau by m, and it is like around 5 into 10 to the power 7. Okay, so that's all. You just calculate it, you will find it out. Okay.
So one simple problem itself will take that much time, is it?
Yeah, but if you have calculator and all, it will be easy only.
For exam, they allow calculator?
I don't know how the exam mode is, if it is online, offline, or I'm not so sure. But I think you can do order of estimates. For example, here, this is how you can do. N is equal to, they will give you such numbers. This aluminum is so intelligently chosen that it will not take into 3, right? So you can forget about this 0.023, you can just 2.7 by 27, it is just 1 by 10, and 6 into 3 is just 18 into 10 to the power 23. You can think of it as 1.8 into 10 to the power, sorry, it is 29. So that's it. It is 18 into 10 to the power 29. You put it here, 1.8 into 10 to the power 29, and it is what, e square, right? E square is 1.6 whole square. 1.6 is 2.56 into, you can think of it as 2.5, this is minus 19, so minus 38. E square tau is 10 to the power minus 14 divided by 9.1, so you can take it as 9 only, into 10 to the power minus 31. So if you just see, say 9 into, this will be 0.2, so this is 0.2, and this you can think of it as 2.5, so you can think of it as 2 into 2.5 is 5,
Plus 8.
0.5 into 10 to the power 29 minus 7 minus 14. Okay, 29.
31.
Yeah.
Plus 31. The top it is plus 31.
Huh? Yeah,
The
plus
top
30,
it was
minus 38 minus 31. This I have written minus 7. So it is
minus
5 into 10 to the power 29 minus 7 minus 22, which is 5 into 10 to the power 7.
7.
Okay, so this is how you can calculate. I mean, you just don't have to think of it as 9.1 as 9.1 exactly. 9, you can think of it as 9. Cut this 2.56, we like I ignored this guy and took it as 2 into 2.5, that is 5. So if you just like have a little bit of practice of this, you can easily figure out. Okay, so your correct answer is 10 to the power 7. Okay, now here this is a conceptual question. You can tell me what would be the correct answer.
So, essential part of an air conditioner as it maintains the balance between warm and cool air by replacing the basically blower. Blower is typically
It will agitate the, it will make the atoms to move, right? That is the process of
convection, right?
convection, correct. What about this? Now you see here it is a positive charge and you want to calculate the mean free time. So Vf is equal to E tau over m. Tau is nothing but m Vf over E, and Vf is what? Nf E A, sorry, is equal to, you remember this formula, right? This came from?
Yeah, I remember. He just showed me.
Yeah.
But I don't remember.
Yeah, okay. But yeah, you just maybe go through. These are the basic formula. This is nothing but J is equal to IA is equal to and yeah, you can just go through these formulas, okay? And these are like quite handy. If you know them, you can solve the problems very quickly.
So mean free time we have to calculate this tau. Tau is
Yeah, it is, see, what is important here? mass is there, electronic
Positive
charge is there, electric field E is there, Vf is there. We have calculated the same thing for an electron. It is just a positive charge, just another situation, and the mass is 9.1 into 10 to the power minus 31 kg. You something clicked in your mind? We just calculated it few seconds before. Somewhere here. Tau. This calculation, same thing.
10 power minus 14.
Yeah, it is 10 to the power minus 14. The same calculation.
Yeah, given getting positive, they have, I was thinking only about that, but they have given the same value for positive also.
Yeah, the mass of electron
So,
positive, yeah, only the mass would have changed. So it is 10 to the power minus 14 seconds. Okay, what about this?
so because, yeah, but two cylindrical rods A and B are made up of same metal and have same lengths but different diameters. The two rods will have same length but a different diameter. Okay, L by A. So, resistivity R. So L by A. So length is same but diameter is different. Area will be different then. Means resistance will be more. Oh no, this will be less. Different resistance or different resistivity, both are right.
Different resistance and different resistivity.
Yes.
See,
So
how
resistivity is constant. Yeah, correct. Sorry.
it is
Same resistance.
same resistivity. Yeah. What about this?
Heat exchanger in your laptop is a combination of copper metal tubes and fans because copper is good electrical conductor. No, thermal conductor. That's the right word. Copper is a good thermal conductor. Uh, so copper conducts the heat and the fan blows it out, brings in cool air. That is correct.
Yeah, cool. Yeah, it is because here electrical conductivity, this statement is correct, but not in this context because the heat
Purpose
exchange.
of
Yeah. So we have to, the correct answer will be this and this. Okay. Okay. How does a free electron exchange energy in a solid?
free electron is typically by conduction,
Uh,
collision, conduction and collision.
say conduction is the process of heat transfer. So, and electron is the medium which will transfer the heat. Okay.
Yes.
I mean, so it doesn't make sense to say, uh, it doesn't make sense to say electron is giving energy to the other electron by means of conduction, because
Okay, it is only the
yeah, you got it right.
yeah. So
So
lattice vibration and collision.
uh, it is free electron. Free electron, how it can? It is, we studied right that the
No
only
collision, no
it
no
is,
collisions. Yeah.
yeah, it is only collisions. Somewhere you had written. It is just by we. This is a very important this part. By means of collisions only, it is exchanging the heat.
So that's the only answer. Okay.
Yeah. So it is this.
Lattice vibration is also not there.
Yeah, lattice vibration.
Why we don't?
Free electron. So okay, in reality there is some electron phonon coupling, it is called, but the probability of this is very less. This is not the major mechanism. Electron phonon, so they will interact. Phonon is nothing but the lattice vibration. So
Yeah.
electron, so the major mechanism is a free electron will collide with the other free electron, at least in the context of Drude-Lorentz model. It is just by collision. So because in Drude-Lorentz model we are imposing the rules of ideal gas, and in ideal gas what happens? One gas molecule will collide with the other gas molecule and exchange energy. So it is just collision. Okay. Okay, what about this? This is interesting.
Different transfer is the ratio of electrical and thermal conductivity. The Truman law is successful theoretically predicting this law because two wrong experiments compensate each other.
Yeah.
That is one correct.
Yeah.
It has theoretical current in online. Now it has only very minor errors in it. A significant. Uh, it has very minor errors in its estimates. Should we consider that?
No, Whiteman-Friends law, it is an experimental error. Sorry, it is an experimental. Uh, it is an experimental thing. So the experiment has been, if it has been carried out very carefully, then there would be no mistake in its estimates.
Yeah. So then there is no errors. Is it?
Yeah. So this is the. It has significant experimental error. This is wrong, and yeah. So this first option is the only correct one. Okay. What about this?
The rod is maintained with one end hot, another end cold. Following its hot position. Temperature is the function of motion along the rod.
Yeah,
Correct.
this
That
is
is true.
correct. Temperature is
Energy of the position along the rod. Energy will be same. Uh,
energy of the electrons is a function of position along the rod. You remember this,
it's
right?
not
Energy was a function of temperature. Temperature was a function.
minus V, minus VT and plus VT. Right?
Yeah. So what is this? Energy of the electron is a function of. Is it correct or not?
Position, temperature, and position. Yeah.
Yeah.
So energy, they are then both. Temperature is a function of electron density at that position. That is not right.
Not right. Correct.
Energy of electron is a function of temperature at approximately position the electrons.
Ye-
Correct. That is true, right?
Yeah, that is true. So this statement actually means temperature is a function of position along the rod. Energy is a function of x. That is true, but only by means of. So this means energy is a function of temperature at x. So
Yes.
it is true. These two statements are same. Okay, so that's all. I hope it was okay.
Yeah. Thank you, sir.
Yeah,
This was
thank
really
you.
good. Actually, I'm getting privileged to attend the one-on-one.
Yeah, thank you for joining. We'll meet next week.
Yeah.